Hi everyone, I am Vishwanath. In the previous two videos, I already discussed about Gauss theorem and its proof and Coulomb's law. Today, I am going to discuss about the application of Gauss theorem. Okay. At first, we are to find out the electric field intensity at a point due to a infinitely charged straight wire. Let us consider it is a positively charged metal conductor, that is, it is uniformly charged conductor, and linear charge density of the straight conductor is lambda. Let lambda be the linear charge density of the straight wire which is infinitely extended. Which is infinitely extended. Now we have to find out the electric field intensity at a point P. The distance between the wire and the point P is R. That is, it is a normal distance. To find out the electric field intensity at a point P, we consider a cylinder having radius R and the axis of the cylinder is the wire, charged wire. Now this cylinder acts as a Gaussian surface. Now the electric lines of force emits from the charged wire is normal to the wire, that is along the direction of the radius of the cylinder. Okay. Now we can apply the Gauss theorem to this Gaussian surface or to this cylinder. Let L be the length of the cylinder. Therefore, let L be the length of the cylinder. L be the length of the cylinder. So therefore, the net charge confined in the cylinder is Q is equal to L into lambda, because lambda is the linear charge density. Now applying Gauss theorem, we can find closed integration of E dot ds is equal to Q by epsilon g. Here we consider that the wire is placed in air, therefore the constant is epsilon 0. Now the direction of the electric field is E along the radius of the cylinder. Therefore, the direction of the electric field and the area vector are parallel to each other. We know that area vector is acts normal to the surface. Therefore, along DE, ds also acts. That is, D and ds are parallel. Here, DE is parallel to ds. And magnitude of E is same everywhere on the everywhere or every point on the curved surface of the cylinder, and magnitude of E is constant at any point on the curved surface of the cylinder. Okay. Therefore, now we can solve the integration. Closed integration of E dot ds is equal to Q by epsilon 0, or E closed integration of ds. Since E vector dot ds vector are parallel to each other and E is a constant, therefore E can comes out from the integration part and we can only integrate ds. And we know EQ is equal to lambda into L by epsilon 0. Here cos 0 is equal to 1. This term cos 0 appears from the dot product, which is equal to 1. E closed integration of ds means the area of the curved surface, which is equal to 2 pi RL, or E is equal to 1 by 2 pi epsilon 0 lambda by R, or E is equal to 1 by 4 pi epsilon 0 2 lambda by r. This is the magnitude of the electric field at the point P, and direction of E is parallel to direction of R. Therefore, E vector is equal to 1 by 4 pi epsilon 0 2 lambda r into r cap, where r cap is the unit vector of r. I think you understand this expression very well. Now I am going to discuss about the electric field produced at a point due to a uniformly charged sphere. Or uniformly charged hollow sphere. First, hollow sphere. This is a uniformly charged hollow sphere whose radius is r. And we have to find out the electric field at the point P. And now P may be on the surface of the sphere, or P may be inside the sphere, or P may be outside the sphere. At first, we consider the point P inside the hollow sphere. Okay. Let capital R be the radius of a uniformly charged hollow sphere. Sigma be the surface charge density of the sphere, of this sphere. Okay. So therefore total charge of the sphere is capital Q is equal to 4 pi capital R square into sigma. Now we consider a point P inside the circle. Now we consider a point P inside the sphere. We know the charge always lies outside the conductor, outside the outside surface of the conductor. That is, we know the charge always lies outer surface, outer surface of the conductor, conductor. Therefore, when we consider a sphere having radius small r, inside the large sphere, large sphere. Okay, the radius of the small sphere is smaller. P lies on the surface of the surface of the small sphere. Surface of the small sphere. Therefore, in the Gaussian surface, there is no charge. Okay, and here we know that the charge always lies outer surface of the conductor or hollow conductor. It may be hollow conductor. Hollow conductor. Okay. Now, applying Gauss theorem to the smaller sphere, we find out applying Gauss theorem to the smaller sphere, we can write closed integration of E dot ds is equal to 0, because in the Gaussian surface there is no charge. The charge lies outside the smaller sphere. Therefore, E is equal to 0. Therefore, inside a hollow sphere, there is no electric field. Therefore, inside a hollow sphere, there is no electric field. Okay. Now we can find out the electric field at a point outside the sphere. Same figure. Here the point is situated outside the sphere. The distance between the center O and the point P is smaller. This is the figure. Okay. Now we can apply Gauss theorem to the sphere or to the surface, spherical surface. Let the point P is outside the charge sphere. Charge sphere. O be the center of the sphere. OP is equal to small r, which is greater than capital R. We consider uh, another sphere having radius R and center O. This sphere acts as a Gaussian surface. Acts as an Gaussian surface. Gaussian surface. Okay. Now the electric field acts parallel to the radius vector or along the radius vector. Now we can apply Gauss theorem to the larger sphere. Okay. Here electric field at P is E vector which is which which acts along R vector. Now, applying Gauss theorem, we can write E dot ds is equal to q by epsilon 0. This gives E closed integration of ds is equal to q by epsilon 0. Here, E vector is parallel to ds vector. Here, E vector is parallel to ds vector, and magnitude of E is equal to constant on every point on the Gaussian surface. Okay. Therefore, we can write E into integration of 2s is equal to 4 pi small r square is equal to q by epsilon 0. This gives E is equal to 1 by 4 pi epsilon 0 q by r square, or E vector is equal to 1 by 4 pi epsilon 0 q by r square into r cap, where r cap is the unit vector of r vector and capital Q is the total charge of the sphere. Now we can easily find out the electric field on a point on the charge sphere. That is, when the point P is on the charge sphere, then small r is equal to capital R. Therefore, capital E vector is equal to 1 by 4 pi epsilon 0 capital Q by r square into r vector. Okay. Now we can draw the electric field versus distance graph from the center of the charge sphere. OX and OY are the two mutually perpendicular vectors. Along X we denote the distance of a point P from the center of the sphere, that is R, and along y-axis we denote the magnitude of electric field at that point. We know that inside the hollow sphere there is no electric field. Therefore, when small r is less than capital R, then there is no electric field. On the surface of the charged sphere, there is maximum electric field, that is E0. That is E0, maximum electric field. After that, when small r is greater than capital R, then the electric field will be inversely proportional to the square of the distance. This is the graph between electric field and position of the point. Okay. Now we have to find out the electric field of a uniformly charged solid sphere. Electric field at a point P due to a uniformly charged solid sphere. Okay. Let us consider a solid sphere which is uniformly charged and charge density, that is charge per unit volume of the sphere, is rho. Because it is a solid sphere, solid conducting sphere or solid sphere, therefore inside the inside the sphere charge can lie. Okay. Capital R be the radius of the sphere and O is its center. To find out the electric field at a point P inside the sphere, the distance between center of the sphere and P is smaller. This is smaller. Now we can draw a concentric sphere having radius smaller, which center is at O. Okay. Let capital R be the radius of the sphere. Therefore, total charge of the sphere is Q is equal 4 by 3 pi capital R cube into rho, where rho is the volume charge density. Volume charge density. Okay. P be a point inside the sphere at a distance smaller from the center of the sphere. Okay. Now we can draw now we can draw another sphere having radius smaller, which is less than capital R, and center is at O. This sphere acts like a Gaussian surface. This sphere acts like a Gaussian surface. Gaussian surface. Okay. Let capital E is the electric field at the point P. Let capital E is the electric field at the point P along the direction R vector. Okay. Now we can apply the Gauss theorem to this Gaussian surface, and we can write closed integration of E dot ds, where ds is the area vector, q by epsilon 0. Here E vector is parallel to area vector ds, and small q is the charge inside the smaller sphere. Therefore, small q is equal to 4 by 3 pi small r cube into rho. We can write the value of rho in terms of capital Q. Therefore, 4 by 3 pi r cube into capital Q by 4 by 3 pi capital R cube. Therefore, small q is equal to small r cube, small r cube, capital Q by r cube. Since capital E is constant at everywhere on the Gaussian surface, therefore capital E can comes out from the integration. Now we can find out the value of this integration and putting the value of small q in terms of capital Q, we can write integration of ds is equal to small r cube capital Q by r cube into epsilon 0. This gives E into closed integration of ds is equal to 4 pi small r square. This gives E is equal to 1 by 4 pi epsilon 0 capital Q by r cube into small r. Therefore, E vector is equal to 1 by 4 pi epsilon 0 capital Q r cube into small r vector. Okay. From this expression, we can easily find out the electric field at a point on the charge sphere, on the surface of the charge sphere and outside the charge sphere. That is, when the point P is on the charge sphere, then small r is equal to capital R. Therefore, E vector is equal to 1 by 4 pi epsilon 0 q by, here we can put capital R instead of small r. Therefore, r cube into r. Therefore, E vector is equal to 1 by 4 pi epsilon 0. Magnitude of E vector is equal to 1 by 4 pi q by r square. Okay. And when the point P is outside the sphere, then small r is greater than capital R. When P is outside the charge sphere, then small r is greater than capital R. Therefore, capital E vector outside the sphere is 1 by 4 pi epsilon 0 capital Q by small r cube into r vector, or magnitude of E vector is equal to 1 by 4 pi epsilon 0 Q by r square. Okay. Now we can draw the electric field versus position vector from the center of the solid charge sphere. OX, OY. We know that electric field intensity inside the solid sphere is directly proportional to the distance from the center of the charge sphere. Therefore, inside the charge sphere, the graph should be straight line. Here, smaller less than capital. On the surface of the charge sphere, the electric field intensity is maximum, which is equal to E0. After that, the electric field varies with the square of the distance from the charge sphere. This is the graph versus electric field and position vector. Now, I am going to derive the Coulomb's theorem. Okay, it is not Coulomb's law, it is Coulomb's theorem. Let us consider a uniformly charged surface whose surface charge density is sigma. Because it is a uniformly charged surface, therefore electric lines of force emits to the normal direction from the surface. We have to find out the electric field intensity at a point P near to the surface. Now we can consider a small cylinder whose area of cross section is A, or area of cross section is A, and is area vector is proportional, is acts along the direction of the E vector. P is the point on the circular surface of the cylinder. Let there is a uniformly charged surface whose surface charge density is sigma. P be a point near to the very near to this surface. Capital E be the electric field intensity at P. Now we consider a normal cylinder. Now we consider a very small normal cylinder whose surface area or circular surface area is A. P is on the circular surface of the cylinder. Circular surface on the cylinder. Okay. Here this cylinder is embedded on the charged surface. Okay. Or this cylinder is on the charged surface. Now this cylinder acts as a Gaussian surface. Q be the small q be the charge on the circular surface of the cylinder. Small q be the charge on the circular surface of the cylinder. This portion of the cylinder contains the charge. Here Q is equal to A into sigma. Here Q is equal to A into sigma. Now, applying Gauss theorem, we can write closed integration of E dot ds is equal to Q by epsilon 0. Since E vector is parallel to ds vector and E is constant on the circular surface of the cylinder, therefore E closed integration of ds is equal to Q into epsilon 0. This gives E into A into sigma into A by epsilon 0. This gives E is equal to sigma by epsilon 0. This is the electric field at the point P. Now we can find out the electric field intensity by a charged plate which is infinitely extended. This is a uniformly charged plate which is infinitely extended and its surface charge density is sigma. Now the electric lines of force comes out from the conducting surface from both ways. Therefore, electric field at a point P near to the surface. Similarly, we can draw a cylinder Here, applying Gauss theorem, since that there are two open surface, therefore E is equal to electric field E is equal to sigma by 2 epsilon 0. This is the electric field at a point P near to the infinitely extended surface, sigma by 2 epsilon 0. Because yeah, 2 is divided, because there are the lines of force comes out from the two open surfaces. This is the end of our discussion. If you like my videos, then please click the like button and please subscribe my channel and please share my videos so that I can reach the more students. Okay, thank you. Have a nice day.